3.1 notes, the start of Chapter 3. We're talking about describing relationships. We're going to be looking at scatter plots and linear regression. So the first vocab term you need to know. If we're talking about two variables, we're describing two variables. That's a fancy way, or a fancy way to say that would be bivariate data. So when you see that word, don't be afraid. That just means we're going to make scatter plots with something on the x-axis and something on the y-axis. So that's bivariate data. The definition for a scatter plot, it shows the relationship between two quantitative variables measured on the same individual. So height and weight, for example. The values of the explanatory variable appear on the x-axis. And notice the emphasis, explanatory, x-axis. The values of the other variable appear on the y-axis. That's the response variable. And then each individual we plot as a point on the graph. So that's your formal definition for a scatter plot. So what's the difference between explanatory and response? So now you know explanatory goes on the x-axis, first of all. But we actually learned this in Chapter 4 already. So for an explanatory variable, that explains, or it's the thing that causes the outcome. Otherwise known as the independent variable. The response variable, that's the predicted outcome. Otherwise known as the dependent variable. And why do we even care? Why do we study relationships between two variables? And we've already made dot plots for one variable. Now we're going to make scatter plots for two variables. Well, the whole point is we can make predictions, we can explain phenomena, and then we just use it as a mathematical model to model situations. Okay, so how do you make a scatter plot? And I think you probably know this by now and you'd probably be all good with it. But let's give it a few directions. So first you need to decide which variable goes on which axis. The explanatory variable goes on the x-axis. Once you got that down, you're probably pretty good. Make sure you label and scale your axes correctly. And then just go ahead and plot the individual data values. How about the easiest way to lose points when you're making a scatter plot? You have this beautiful looking graph, points are plotted perfectly, you used a ruler, everything looks good. Easiest way to lose points on the AP exam or for an AP Stats test, forgetting to label the axes. The easiest way, hence the comic below there. Let me just scroll down here. How do you know which variable to put on which axis? Independent variable goes on the x-axis. That's our explanatory variable. Therefore, the response is the dependent variable. That goes on the y-axis. So it depends on the explanatory variable. That goes on the y-axis. And then where do you start each axis? Well, just like we looked at in the activity, it's not always at 0, 0, especially if you want to have a visually appealing graph that makes a lot of sense and it illustrates the situation well. It doesn't have to start at 0, 0. A reasonable way to find where it should start and end is look at the largest and smallest values and see how high and low you're going to go on each axis. So let's look at our first example here. This is, I think, the only actual scatter plot we're going to make in these entire notes. So let's make one well. Let's do it right the first time. We won't make any more. We'll let our calculator do the work. But this should be pretty simple. 12 stat students in a class. We're going to look at their 40-yard dash time, how fast they are, and how far they can jump, so their long jump distance. The sprint times in seconds, that's up here. And then long jump distance, that's in inches. Okay, so sprint time, we're going to say, is the independent variable. That's the explanatory variable. How fast you are explains how far you can go in the long jump. Okay, so that's what we're going to use as the explanatory variable. So sprint time will go on our x-axis. Long jump distance will go on our y-axis. Let's get our axes down here. Now, when we think about how we want to scale these things, we're not going to start at 0, 0. Think about the lowest and highest sprint times and the lowest and highest long jump distances. So what is that? lowest 5.05, highest 7.25 for the sprint. And then 184 and 65, those are max and min values for the long jump distance. Okay, so I'm going to scale my axes. For the y-axis, I'm going to go from 60 to 180. That should account for all those values between 65 and 184. And then 184 I'll just put above it a little bit. And I count by 20s. Y-axis seems reasonable. We'd go from about 5 to about 7.25. So that's the maximum about to the minimum. And then let's just count by 0.25. This is the x-axis. And then do not forget to label these. Sprint time, that's in seconds. And then the y-axis, that's long jump distance, that's in inches. Okay, now just plot each individual and see what we come up with. So I try to do it as accurately as I could. So 5.41, 171, 5.05, 184, 7.01, 90, so on and so forth. Let's see if we can get all of these stats kids down here. Okay, so you should have 12 dots. At this point, this looks pretty good. Hopefully yours stacked up like this. Maybe yours looks better, a little more balanced. But mine will do for now, and it's got a little color to it. Okay, so what are we going to do with this thing? We'll come back to it in just a second. Since we got our dot plot constructed, or not our dot plot, our scatter plot constructed, we'll come back to this in just a second. Because we need to be able to describe this, and I haven't given you the tools yet to describe this. So you remember from chapter 1, we use SOCS for like dot plots. We shape, outlier, center, spread. So I got a new acronym for you, and I'll give it to you in just a second. So let's scroll down here. The 4 characteristics you should consider. The first one is the direction for the scatter plot. So what direction is the trend heading? And think of it like slope. It can either be positive or negative. Positive or negative direction. So, for example, a positive relationship between hand span and your height. Okay, so that's the one way and one of the components we're going to use to describe these things. The next one is the form. And when I say form, I mean you need to comment about, is it linear? Is it non-linear? Is it for sure curved? We just need to comment about what the trend starts to look like. And just a little hint here, don't let 1 or 2 points fool you. Look at the overall trend in the big picture. If there's a couple points off, that's going to be okay in general. So zoom out, look at the overall trend before you make any judgments about form. The third thing we got here is strength. Strength means how closely it follows that form. So how closely the points follow the form. Like if they're all in a perfect line, that's a really strong relationship. If they're kind of scattered and all over the place, well, that starts to be kind of a weak relationship. So, for example, how would you describe the strength of the association? Well, you could call it weak. You could say it's moderate. You could say it's strong. You could say moderately weak, moderately strong. Those are the typical descriptions for strength. And the last one, and this is the same as chapter 1, is you got a question, are there any outliers? And there may not be, so you may not have to mention it, but if there are, you need to note, are there any outliers? And those are the points that strike far outside the overall pattern. Okay, are you ready for the acronym? There's direction, there's form, there's strength, there's outliers. So the acronym we're going to use is DOFS. D-O-F-S. DOFs. So when it comes to describing scatterplots, direction, outliers, form, and strength, say something about each of those. Maybe not outliers. There's no outliers, you don't have to say anything. But it's kind of like socks, except for this is for bivariate data, scatterplots. Okay, so let's use this idea to describe the track and field example. Let's take a quick look back at that graph. So the overall trend, it looks like it's going down. So I would say a negative trend, and it follows a line decently well. I mean, they're definitely not perfectly in a row, but it's obvious that there's a somewhat linear trend going through here. So, using the tools, let's go back to where we were. We can say it in one sentence if you're really good at this. So, there appears to be, because we didn't actually do any calculations yet, so there appears to be a moderately strong, negative, comma, linear association. So it was moderately strong, it's pretty obvious. It was definitely negative, and it was, we're suggesting it's a linear association. Okay, one thing I want to point out here, definitely put a comma between these descriptors here. Okay, because if you write moderately negative, that's absolutely incorrect. There's no such thing as being moderately negative. You're either negative or you're positive. So don't confuse those. You can be moderately strong or moderately weak. But we either say it's positive or negative. Don't start calling it moderate negative or something, okay? And to give it some context, the association was between sprint time and long jump distance. For what group? Well, it's for this class. So that is a point in itself, the fact that you give it context. Did we account for all the characteristics of DOFs? Well, moderately strong refers to the strength. Negative, that was referring to the direction. So S and D are good. And then the linear part, that was referring to form. And since there weren't any outliers, I didn't note them. I mean, we could have definitely said there don't appear to be any outliers here. One last little bit I want to point out where you can gain or lose points. That's the context piece. So you use words from the problem when you answer this question. So that's critical also. So in general, what's the trend look like? Well, it kind of shows that the slower your sprint time is, the shorter your long jump is, which should make sense. All right, that's good for the track and field example. Last example here. Going back to the McDonald's nutrition data. Seems like we use that a lot. Guess they have some really obvious patterns. So this is sodium versus fat, and it's in their salads. Okay, so a couple things you should notice. Yeah, overall, definitely going positive. And really, there's no outliers. There's no like one person that broke way off above or broke way off below. There's really no outliers. I know that there's like a group and a group like kind of broken up. It's almost like there was a line and these three like broke off down here. But there's really no outliers. So that's one, we could note that. Even though it might be broken, there's no apparent outliers. But is it linear? And the answer is no. This is definitely not a line. It goes there, breaks off, goes here, comes back, goes here. This is definitely not linear. But the trend is positive overall. Like the more sodium you eat, the more fat is in the salad. So there's definitely a positive association, meaning that salads with more sodium generally have more fat. And the overall trend is definitely nonlinear here. It's definitely nonlinear. But the association itself is actually moderately strong. because the points don't deviate far from the pattern that it's on. I know it's not linear. I know it's not a linear pattern. But whatever pattern it is, right, there, then broken, it's here, and then broken, it's here. It does follow it really well. So it's still moderately strong. That's how I would classify the strength. But it's just the form would be nonlinear. Okay. And one thing I want to note, and you may be able to figure this out on your own, especially if you have the McDonald's menu in front of you. There's 3 distinct clusters of points here. Okay. And essentially they represent 3 kinds of salads. It has to do with chicken being in the salad. Okay, so there's 3 distinct groups. I'm going to color code them. This group's green, blue, orange. If you look at the menu, you probably figure this out yourself. But in green, that's the salads with no chicken at all. So no fat, no sodium. Blue, that's a salad with the grilled chicken. Orange, that's a salad with the fried chicken. So notice how well those groups are related to each other. So that's why this graph looks this way. Okay, so the point is that within each cluster, there's definitely like a strong positive linear association. If you look at each cluster individually among themselves, there's a strong positive linear association. In my context for the situation, the association between sodium and fat. Okay, I want to make sure to get one example in here where it's a little weird and it wasn't linear at all. And that was this example with the McDonald's data. All right, that's all for these notes. I'll see you in class.